We know that the work done by a force F on a body is W is equal to Fd cos theta, where d is the displacement of the body and theta is the angle between the force and displacement. But in practical situations, a body may be acted upon by a force which may not be constant and is a variable force. A variable force is a force whose magnitude or direction or both vary during the displacement of a body on which it acts. Let's look at an example of a variable force. As the spring oscillates between the extreme positions O and A, the restoring force on it keeps changing with the displacement from the mean position. This is a variable force on the spring. How do we calculate the work done by such variable forces? Let us suppose that a body moves along the direction of a variable force acting on it. We then plot a graph of force F versus displacement x, which helps calculate the varying force with the displacement. The work done by the variable force can be found by calculating the area under the graph. To find the work done by this variable force, we divide the total displacements into n number of small elements or segments: delta x1, delta x2, delta x3, and so on till delta xn. The work done with respect to the first segment, delta x1, is the area of this first segment, that is, F1 into delta x1. Work done with respect to the second segment, delta x2, is the area of the second segment, that is, F2 into delta x2. For the third segment, delta x3, work done is the area of the third segment, that is, F3 into delta x3, and so on. Here, we assume that the force remains constant for each small segment. Thus, the area of any segment will be denoted by the expression delta A is equal to Fx delta x. Let this be equation 1. The total work done is equal to the sum of the areas of all the small elements, which is equal to the summation of F delta x taken within the limits from x1 to xn, as in expression 1. If the size of each segment is very small, each segment